Yeah, Michelle. Bro, Michelle. Bro, did he have he had ate last night? I don't know what bro was on. I think I skipped one this morning. Sorry about that. No, that's what I think your name was like, wait, is this double space or single space? Yeah. I know, right? I barely use this for doing documents, so I don't know how it works. I was using one, but I couldn't get it to like sign on for something. So I'm just like, screw it, I'll I'll just copy and paste it back. This is why I didn't want to do formatting, because I knew this was gonna happen.
So as you come in, you can start warming up on this problem, and then we'll go over it. And then we just have review planned today, so if you have questions as well, we can go over things. I see some answers, so let's start going through this. So does someone want to put it on the board, maybe over there? We have to erase all that lovely work. Anybody need this? Okay, bye. So nice. Oh, I'm too short. That was like a really nice cylinder too. See, does someone want to at least start us off, or maybe how to set it up, what we did? Volunteers. Alero, you
I'm
look
still
you look
filtering into my
extra
calculator,
excited.
otherwise I would.
Well, I'm new here, because I'm a new savvy at the moment, so my report's not be able to project even less so than what it is.
I mean, I've got an answer, I don't know if it's right or not, but.
Go for it, and
Alright.
then we can.
So just over.
Yeah, let's do it over there. And
So first off, we have our equation. So we're given initial concentration for KX5. So I've got 1.5 right there. 0 moles for those two. So reaction initial equilibrium. So our X right here, since we've got nothing over here, it's all going this thing on this side. Negative X, positive X, positive X. So this would be 1.5 it's like yeah, okay.
Yep.
It was there. I'm just like trying to figure out which one it was. So we can set up our case E is equal to case E equal to x squared over 1.5 minus x. Can equate kc is equal to 0.0511 is equal to squared over 1.5 minus x. Basically, to get rid of that, multiply that on this side, and I've got 0.07665 minus 0.0511 x equals x squared. I rearrange that so then I get x squared plus 0.0511 And so that would mean that our AX3 is equal to 0.252. Over A, is that, it's X2, right? X2.
No, it's just X.
Was it X2? Okay. Okay, I'm a little confused. Why is this AX5 and AX3 and then just X2? Is there any particular reason for that, or?
Just the chemicals,
Oh,
or, because
okay.
they're fake chemicals.
Gotcha. Okay. So I was like, why is there something here? Okay, so then that's X2 is equal to 0.252, and then I end up when I subtracted this 0.252 from that. Which one did that one? It was like, oh, I think it was like 1.24.
That looks good.
That's good.
Did anyone have any questions? I'll kind of go over it for the online people. But basically, the key point was our equilibrium and then setting it to KC. So did everybody follow with that? Just kind of checking. And if you don't, right, speak now or forever hold your peace for the final, because this will be on there doing the equilibrium problem. And then thank you, Trenton, for walking us through the math. So, right, everybody followed that. So just distribute everything. So multiply by this across. And then quadratic, which you could plug in to the calculator if you needed help with that. And then, of course, solving for equilibrium.
I do
Yeah.
have a question. How many equilibrium questions will be on the test? Because we've gone through this a lot.
How many? Let's see. So there's a pH problem, which we'll practice. There is something that you might recognize would look like this scenario, but you'll see what chemicals I'm talking about as opposed to X's, and numbers will be different. So 2 at least. Yeah, I think just 2 actually. Unless I change the exam somewhat, but that's not my intention. I want to add just more multiple choice questions to the exam. I think I put too many free response on the midterm, so I'm going to try to do more multiple choice, and they should kind of look like the last 2 quizzes without typos, hopefully. So that's my plan for the midterm. So on that note, let's do one more equilibrium. Oh, sorry.
Midterm, on the very back, you did the orbitals question. Are we going to have a similar question to that?
No, so there's no orbitals on the finals or anything. So I apologize for people that love orbitals. But I just left them off, so it's a lot more math and equilibrium and those formulas. And we'll go over the other types of questions that are on there. But since we're in the equilibrium mood, let's do another one. And so similar but different. And so let's calculate the pH of a 2.3 molar solution of our cyanic acid, and it has a Ka of 4.9 times 10 to the negative 10. How are we feeling about this one? Does someone want to try to put it on the board for us? This one, the map shouldn't be as bad because we have this factor. So I'd probably make some assumptions. Or you could work it out, depending on how excited you are. Anybody want to try? How are we feeling? Riley, do you want to try it?
I don't think my answer's right.
We could see.
Hold on, wait. I know how to get the right answer. Where do I do it?
Let's put it on the front one if we can squeeze it in there. Or we start erasing, and then I think you have to steal a marker from that side. I'm not sure why. There's a black one.
I got it.
And so you could walk us through too.
Yeah. So, I have the reaction thing, and then the 2.3 starting at the HCN, and then negative x, and then 2 positive x's, and then that makes this one the 2.3 minus x, and those are still just x. And then the 4.9 times 10 to the negative 10. And then I have the x squared on top over 22.3 minus x. And then when I multiply that to the other side,
So you could take an assumption here. So it sounds like you did the quadratic, so.
yeah.
So that is fine. I just want to note that right with this factor, we can probably assume that x is very, very small. And so if you went on to solve it like this, then that's fine. So I just want to put that in. So we should get the same number. So yeah, go ahead, tell us what you got.
Just for x?
Yeah, so you can walk us through the math too, because there's nothing wrong with what you did. It's just
Okay.
more precise.
Okay. Well, then when I multiply those, I have x squared is 1.127 times 10 to the negative 9, minus the 4.9 times 10 to the negative 10x. And then adding it all to the one side. took the negative log of that. Cause that's the H plus number, and I got 4.47.
So that sounds good. So did everybody do that? And I got this exact same number making the assumption when I did it on my work. So that looks really good. So questions about this one? And so everybody saw the setup, kind of like before. And then again, we could have assumed, or Riley walked us through the math. Questions about these equilibrium problems? So I don't see anything.
Oh, wait, but, could we do one of those ones where there's two steps, those ones?
Where you have like two initial conditions and stuff?
Well, I don't know about two initial conditions.
But
just
like,
you have to, the ones with the acids where you like have multiple.
Oh, like a,
Yeah.
maybe we should say that, because it won't be on your exam. So we
Oh.
could, I don't mind doing one, but let's do the other stuff that will be on your exam, yeah. Because those can get kind of convoluted, like from your homework. But, yeah, there are no triprotic acids on the exam of equilibrium like that. I didn't want to confuse people. All right, so let's try another one. So one of those equilibrium ones. So now we want to find our equilibrium constant for this reaction. And we are given the following. Let me switch colors, actually. Yeah, 2.22. So let's at least start hearing your thoughts. So how could we add these two equations to get our one up here?
You have to multiply the purple ones by 2 to then be able to get the same values as the top one.
So multiply by 2, and then do we need to flip any of them, or? Flip the second one I'm hearing? The second one or the first one? Or you mean like second one as in first purple? This one? Okay, sorry. So let's see. So you said times 2 and flip for this one. So let's, oops, oh my gosh, shocked myself. So let's see, 2a2b2 gives us 2a2b plus 2b. And so if we flipped it, then that would be 2.22 to the negative 2, right? And so now doing the second one, so you said times 2 again, so 2a, oh, sorry, 4a. 4a plus 4b gives us 2a2b2. And so that means that's 10.5 squared. And so let's see if this adds up. So these cancel, and then we have 2b. So this becomes 2b. And so I'll just rewrite it. So we're giving back, so 4a as a gas plus 2b gives us 2a2b. So that looks good. And so now we can multiply these two. So then that means our Kc for this reaction is 10.5 squared times 2.22 to the negative 2 power. Oh. And so what did people get? Sorry, firing up calculator. So I get 22.4.
Oh, I also got that.
So excellent. Questions about that one?
Can I scroll up just a little bit?
Yeah.
So to kind of like recap, because it's been a little while since we've done these, and I'm not super familiar with them. Basically, how we solve for the first one is we want to take whatever parts, we want to basically equate another one using constants to the top one.
Yeah, so we're just trying to figure out, right, what system of equations. And of course, right, we're limited by what we're given and what we have the Kc of. But in theory, right, this could apply to another scenario where you want to figure out, you know, the Kc of whatever reaction, but then maybe you know the Kc of other reactions. And if you add them and can get to that reaction, then you can find your equilibrium constant. Other questions, thoughts?
Could you go over like canceling them out again, like when you multiply them out and then like cancel them? I guess I just got confused.
Yeah, this one was a little funny because we have a bunch of B's everywhere. But I guess part of what I've recognized is, okay, we're looking at this, but then we have this weird A2, B2, right? And we have them in both of these equations, but they're not in our added equation. So that's telling me, right, I'm probably going to have to flip something. And then, well, we have A's and B's, and then this has a B, but not an A. So I think that's why most people were thinking to flip this one. And so that's where it got flipped, and then people multiplied it by 2 to give us our 2A, 2B here. So I think that's what gives you the most hint. So then that's what happened there. And so some of it is you just have to kind of work it out, right? So just try it. And so, right, we flipped it, multiplied everything times 2, so we still have this weird 2B for now. But then go ahead and add the other one. So again, times 2, so we have 4A, 4B. And so that's where we started crossing out. So you cross out anything that's on the same on both sides, so that's why these two terms went away. But then we had this weird 2B and 4B. So this 2B went away, leaving us with, so minus 2B, and then 4B minus 2B. So leaving us with 2B, which is what we were looking for. And then once we can add them, then we just multiply the two KCs, which we had to manipulate based on our flipping and multiplying. All right, let's try another one with those other equations. And so let's see, we're looking at this basic reaction of 2A going to B, and we are given that it is second order in A with a rate constant of 2.8 times 10 to the negative 2 per second, and this is at 75 degrees Celsius. So how long to decrease concentration from 0.97 molarity to a final concentration of 0.27 molarity? Yeah, and then this is per second. So does someone want to put this one on the board? You can put it on the far board over there. So any volunteers for putting it on there? You don't want to do it?
No? I don't think I have the right. Whoever goes up, I'll assist.
Yeah, I'm sure you could start us off just fine. We could figure out what's wrong if you do indeed do not have the right answer, but you never know.
All right. I'll take one of the two.
Yeah, that's true. And yeah, you can erase.
I don't wanna erase anything.
Okay.
So, I'm gonna write the equation I used, and then you can tell me if I'm wrong or right.
All right, that sounds good. By me tell you, we'll see with the class.
Yeah, yeah. Right?
I like it.
Okay, cool.
Any objections so far? All right, yeah, keep going for it then.
All right. That's what I got.
Oh,
Although my time doesn't look right, so I think I did the math.
I feel like there's just a little calculator error because everything looks right. So let's punch it in together.
Yeah, it was right numbers, but I think it was like the wrong, like, say,
Maybe.
Did you write 28 times 10 to the thing too there?
I should have. I don't know.
Because up there was 2.8.
Oh.
Yeah, so maybe that's if you plug that
It
in.
was kind of hard to see.
Wait, so it's 2.8?
Yep.
Yeah,
Yeah.
sorry, that was hard to see. So there's supposed to be a decimal, so that will fix your answer.
I was like, why didn't you say?
Blah, blah, blah.
Yeah, that's what I got,
Great.
25.5.
Me as well.
Saturday.
See, you did it.
I knew I didn't have the right answer.
You were close. You were real close.
So any questions about that one? And just a reminder, so it's from the chapter 17, write those notes there. And your big hint was saying, well, it's second order, and so that was a nice equation to
One thing,
use.
if we could go back to the question, by the way. You can go up. You said that basically you have the break constant as inverse seconds.
Oh, but
Correct
it
me if I'm
doesn't,
wrong, isn't it supposed to be inverse, like?
yeah, it should be
molarity?
molarity, you're right.
Okay. That was tripping me up for a little bit. I'm like, am I supposed to do something here, or? Okay.
Other questions, issues about that one? No, fix it. I don't see anything on the chat either. All right, let's take a little break. unless people don't want a break, but I assume you want a mental break. All right, so let's take a little break. We'll do one more problem from your midterm, and then probably we'll do a triprotic acid maybe, if that's what people want. And then we can go over anything else. So, yeah, take a 10-minute break. We'll be back around noon, I guess.
So it's for the magnesium lab. Basically, wasn't it that the amount of magnesium was a 1-to-1 ratio with the amount of hydrogen?
We should go over this one after the break, because a lot of people got that one wrong. But yeah, I can explain it to you
Okay.
now, because basically you're right, it's a 1-to-1 ratio, but the constant was our mass of magnesium, right? And then we were dividing it by moles of H2. So if it broke loose, right, then you have too many moles, right? Because now you have more air in there, and then you're dividing the mass by more moles. So then it comes out with too low of a molecular weight.
So if it leaked out, it would be too high of a?
Yeah, because then if it leaked out accidentally, then we'd have less gas. So then we're dividing by less moles, so then it's too high. But like, I would say probably 90% of the class got that wrong, maybe, or like 85. That was like the one
Because
tricky
I thought
question.
like the air bubble breaking loose, I was like, in my brain I was thinking, well, the gas is still in there, it's just sitting at the bottom, but it's like still, like it didn't change the amount, it's just, was at a different, like it was just underneath the water when it should have been, and then popped up, I don't know,
Yeah.
it just didn't really make sense. Okay, well, thank you. I didn't really understand what happened here.
It was supposed to just be divide, because it gets confusing, right? Because remember, this is 1 over, your y-intercept is 1 over km, and then once you go to recalculate for the value of km, sorry, I think I said that wrong, because I have to look at the lab, but it should just be 0.0106 divided by the 21.
Oh,
Yeah, because you actually need the value of 1 over 21 to plug in. So that's why it ends up that you're dividing by it.
okay.
Yeah. I'm gonna get all my study done tonight. If I have extra time after that, I'll probably do those the last time. The exact same problems and copied it over. You know, all the two-minute problems for the galaxy trip, fucking back in the car. I don't know if you remember, but for whatever reason, he didn't write the equation, so he ended up like just that answer so long. So when he copied that over to the final, only for that
Well, did you get them back?
Yeah, I got him back.
Okay, I think that, yeah, they must have just not gotten saved. I can grab one from the lab. Yeah, let me go grab one.
I hate those. I got 70% in
Write the equation.
You got 70% in clear.
And then afterwards.
I
get it? It was like 4.5. It was like, instead of like the maximum area. Oh. Okay, like, and then you said chapter 20 as well? I should have, but I could have papers sitting here. Oh, yeah, wait. There's your 19. Maybe it just didn't update. Okay. Hand back. One more question.
Yeah, so this is my introduction to my paper. Is this like, can you read over and just see if that's like what you apply? Because I'm not as familiar on how the introduction should be.
No, we've done.
Yeah, the quiz was honestly that was the, he said like the quiz was enough to show,
Yeah, this is a good start. I'd probably add to this just like a structure too, to show that would look cool. But yeah, that's basically the right idea. And then just put your name on it if you're turning it in.
Because the rest of it of like analyzing the articles, I think I'm good on that. But is it okay if we put like structure or like big like bolded letters to help like organize all of it?
Yeah, because usually what you want to do is like put in parentheses, like if you show this and then like figure 1 or whatever, and then have your nice little figure showing. Yeah.
Should I wait to turn in these homeworks until after lab?
I don't. Well, we don't have lab today.
I mean, after this
Oh.
exam is what I meant to say.
After the exam. If you want them to study, then just hang on to them.
It's just because you hand out four separate packets and it costs half of all of them.
trigonometric functions. Yeah.
For sine and cosine, it's been a while.
It's been a while. Like, I mean, as far as the sine cosine, that's
Oh, very consistent.
Consistent, okay, good, good.
That's where, yeah, you
I'm-
shouldn't make us do coefficient rule.
well, we had to product
Oh, man.
So, yeah, we had to do product rule for that. I don't think you've been necessarily doing
Was it actually that hard? Okay.
So, I think it's that, and also the potential.
Yeah, and then the actual difference, what should be, that's the integral, that's the negative.
So basically, because I didn't do that one in the spring class. So basically, it's just, oh yeah, you just go on like say, from this point to this point, and then from this point to kind of form something. Basically, like, say, your origin, you start to whatever place at the bottom, like say your x-axis, that's it.
Then just like over there, perspective.
And then you just add.
And the partial. I don't think it really matters. Yeah, because he might. My only favorite game is right now. But it is the partial.
All right, it looks like everybody's here from break. And so just a quick note, so check your grades. So everything should be graded up to right now. So what y'all handed me last week, I should have graded, given back to you. There could be a few straggling assignments, especially if you emailed them, but just ping me a friendly reminder, check your grades. Sometimes grades don't enter well on Blackboard and don't save, so just double check, and then I'll work really hard to get that in ASAP so you can kind of double check your grades again on Thursday. I'm trying to get them finalized. And then I did want to at least talk about the lab checkout final, because this question was missed by a lot of people, which is fine. So this was written as the trickiest question. I was just feeling really nice and graded really leniently for everybody, and gave people 10-point credit just for checking out, since you guys are awesome and washed all your stuff, and I'm not sure other classes do that, so go us. But let's look at this problem, because this was a tricky one. And so it asks us to think back to that atomic weight of magnesium lab, and it says which error would lead to a mass that is too low. And so we have something that the H2 kind of leaked out of the hole in our rubber stopper, or an air bubble broke loose from the rubber stopper and rose up. And so I think most people recognize, so if H2 leaked out, they were kind of thinking, well, that means that, right, our gas is lower, so our H2 moles is lower. But and then, so versus this one, so our air bubble rose, that means, right, we have too much gas in our tube, so H2 moles is higher. But then the tricky part is we have to think back to the math, because we were given, I'll just call this X, right, which is our constant mass, so our mass of magnesium, and our formula for molecular weight is, right, grams per moles. And so now we can see which one is which. So if X is constant, right? And so that's going to be our grams is constant, sorry. So molecular weight. X is constant. So in this scenario, if the moles is decreasing, right, so then you're dividing it by less moles, so then the error in here would actually be that it's too high, right? So we're dividing it by a smaller number, so now that gets bigger, so now our mass is too high. Versus our air bubble, so if this happened, right now we have too many moles of gas, right? So now H2 moles is too high, so then if we divide by that, then our molecular weight will be too low. So the answer should have been B, but like I said, that was a commonly missed one, and it was, like I said, an intentionally tricky one. That's the one that tricks people year after year, so just wanted to at least talk about it so we all know why. Questions? And I think that was basically it with the lab, or at least with the lab exam. Most people did pretty well. All right, so again, check those grades, check those grades. So let's do the last type of problem that we'll see on the free response. And so this is, so the rate constant for a first order reaction is 4.4 times 10 to the negative 8, and at 25 degrees Celsius. Let me rewrite that 25. And so what is the rate then at 50 degrees Celsius? And we are also given that the activation energy is 1.00 times 10 to the 5th, oh, sorry, really bad fives, but joules per mole. And what formula do you need?
Well, I returned, did you read it? That's not, can't figure out. Oh, I, why, no.
Do we still need a few minutes with this one? Okay, people are still working. So start walking me through. So what formula did we pick?
This is probably not the easiest way to do it, but I use the Arrhenius equation, K equals A, negative translation of G gas constant times temperature. Solve for A is my process, but I do recall that there was a simplified formula for this. I just don't recall exactly.
They do have one at 18-point time, which is the natural log of the K2 over K1 equals activation energy over R constant multiplied by 2 minus T1 over T2 times T1.
Yeah. And you can use this simplified version, yeah. So this is the form that I like. I think there's another form where it like multiplies the temperatures as well, but that one should also work with this. So any 2-point equation. And Alyra, you can let us know if your method worked as well. So yeah, I just plugged this in based off of this data, so solving for K2, sorry. And then we were given K1, so 4.4 times 10 to the negative 8th equals our activation energy times the gas constant that's related to joules. And then temperature just had to be in Kelvin, so 273 plus 25, minus 1 over, so 273 plus 50. And so let's go over this because we have to do a little math. So I'll punch this in.
Does it matter? Does it have to be in Kelvin?
Yeah, so it has to be in Kelvin. So that is the one thing that does matter, unfortunately. Because it's all related back to that thermodynamic relevance, you know, that we have to have a 0 to whatever scale to be positive. And so then I get something like this. So natural log of K2 over 4.4 times 10 to the negative 8th is equal to 3.124. And then from here, do we remember we take everything to the e power so we can get rid of the natural log. And then we're left with K2 over 4.4 times 10 to the negative 8th is equal to, sorry, let me plug that in. Where's my E button? So I get K2 over 4.4 times 10 to the negative 8th is equal to 22.737 or whatever with rounding. And for K2, what do we get for K2 then?
I got 9.96 times 10 to the -7.
That looks good. Is that what other people got? You could have probably rounded to like 1 times 10 to the negative 6 as well. So somewhere around there. Questions? Oh, sorry.
I do have a question, because I know that there was kind of like a, I think it was part of the appendix or whatnot that went over like, say, the natural log, like say rules as far as significant digits. Could we maybe go over that again? Because I kind of very, I guess, don't exactly know exactly how to work with that.
Yeah, so kind of the general, I'll say like general rule. So if we're taking, right, the negative log of our, because generally it's for the pH that we look at this, so like let's just say 1.11 times 10 to the negative 3rd or whatever, I'm just throwing out a value. And so when you put in the number to this, so if you put in 3 sig figs, you just get out 1 more is how to think about it. But I probably won't be too picky with the sig figs on the exam. But so then, right, to round appropriately, now we need 4 sig figs, so 2.945 would be the answer there.
So you just add another significant figure.
Yeah, for our logs, but, so just anytime you do a log, you can add the sig fig, but. Again, with y'all, I'm more focused on like the other parts of the math and everything else. And yeah, there's nothing specifically that tests on like error propagation in this lab, so I'm less picky about it.
So the one you just did, I don't know if I'm doing it wrong, but I didn't get the 9.96 answer. I multiplied don't you multiply the 22.737 times the 4.4 times 10 to the negative 8 thing? I got 1.0004 and a bunch of numbers times 10 to the negative 6.
Yep, that's the same, like rounded, right? Yeah,
I don't know, I started with a 1 and now I started with a 9.
yeah, because you said you got 1.00 something.
Yeah.
Yeah, times 10 to the negative 6. They're like the same number, right? Because you round this up and this would round up to 1 times 10.
Okay, is it just a matter of like the exponent at the end?
Yeah, because it's just a matter of rounding, right? Because you could round this up then, but then if you round it up, that's where you get to the negative 6.
Okay, perfect, thank you.
Yeah.
That's what I was really confused.
Yeah, these are the same.
Okay.
When you took the E of the 3.124, I don't know if I'm just doing it wrong, but I got a different number. Don't you just like put E of the answer and it should do it?
Yeah, well, you put E and then to the power of the 3, right? 3.124. Yeah, and make sure it's like the right E, because I don't know if you could put in like this E accidentally. I'm just seeing what it gives you. Oh, that just gives you a syntax. I wasn't sure. I'm trying to see if there are any other E's you could. Sweet. All right, so that is roughly kind of what I have prepared for the exam. So like I said, there'll be some multiple choice questions, and I'll probably pull those from especially your last quizzes that we had as practice. So there'll be stuff, you know, collision theory basics, the orders of reaction, so like the overall order. Let's just practice one. So right, if you have your rate is equal to K times A squared, B squared. So what's your overall order of this reaction? So 4, so remember that was just adding up, right, your total. So overall 4. And then there'll be some stuff like we might expect, like what happens, you know, when we double something, if it's first order, if it's second order, that sort of thing. If we triple it, if it's first order, second order, so expect that. Maybe Le Chatelier's type of problems like we saw in the quiz. And then probably some multiple choice, right? What's an acid, what's a base with our salts. And then it will just be the free response like we've gone over. So like you guys deduced about 2 equilibrium problems, so one of those being purely in equilibrium, the other being a pH problem. So I think y'all are set. But we can go over, so my thought was to do the triprotic acid from the homework, phosphoric acid, to walk everyone through that one for the end. And if you don't want to stay for that, because like I said, triprotic acids are not on your exam, not even diprotic, you can leave, but otherwise, you know, feel free to stay and learn more. Fun. All right, so let's do your phosphoric acid. So I'm just looking at the homework, and it says to calculate the pH and equilibrium constants for all these concentrations. So our phosphoric acid, our first deprotonation, second deprotonation, and phosphate. And it says for a 0.0325 molar solution. And so this starts off just like we did before, right, where we have to set up each little step and then think about what gets added. So just start with your first dissociation. So that makes, right, H2PO4 plus H plus. And so then we can start, right, so we're given our initial conditions. So 0.0325, and then we'll just kind of leave this for now. And then our change is going to be minus x plus x plus x. But again, we're going to have to come back to this, right? So the problem is then we're going to disassociate again, And then we're going to have more y, so let's do that. Bye. So now we have H2PO4, right, next dissociation. And so, right, this value is equal to x, so now this has initial conditions of x. And then like we did before, so we said, let's just call this second dissociation y. So now this is minus y, plus y, plus y. But then, right, this isn't really just the only h we have. So we have to add in, so plus y over here, but we had x over here initially. All right, so now this looks okay. And then, right, what's confusing, so this is where we went with our diprotic from the last time. But now we have to do it a third step. So now we're starting with HPO4, 2 minus. Now do our last dissociation to give us phosphate. So now this corresponds to Y, right? So that's from here. H plus, well, now we have to add in everybody. And so let's just say, right, this is going to be plus Z. But then we also have X and Y. And then we need to go back and add it over to these factors, right? So H plus also has Z. H plus also has Z over here. So that looks good. Sorry, just double checking. I forgot to subtract this from the beginning, right? H2PO4. So we have minus X, plus X, but then it's also losing Y. And so just filling it back in, so that's okay. That's fine. So now this is Y minus Z, so we have to fix that. See ya? And so phosphate leaves it as Z. All right, so now we finally have everything. And so let's see. So let's start from the top then. So we have all our expressions. And so the other piece of information that we weren't given, but we could look up. So, right, we just have to look up, yeah, so our equilibrium of phosphoric acid. And the problem is you can get different values.
So in the book for phosphoric acid, the pKa1 is 1.3. Oh, shoot, sorry, yeah, I'm looking at the wrong one. 2.16, yeah. Yeah, that's the phosphorus, not phosphor. Yeah, okay, I see. So 2.16 for pKa1.
Oh, wait. Slow down.
Sorry.
So pKa, so then 10 to the power of, what was it?
2.16.
2.16. So then that gives us, because I wanted to put it in Ka, so 6.92 times 10 to the negative third. 6.92. And
The next pKa was 7.21.
so 10 to the power of negative 7.21. So about 6.16 times 10 to the negative 8th.
And then the last one was 12.32.
10 to the power of 12.32, or negative, I should have been saying. So yeah, 4.98 times 10 to the negative 13. And so now we can probably just start at the top, I think is the best place. And so we can set up, right, our equilibrium constant. So 6.92 times 10 to the negative third is equal, so now we have this x plus y plus z times x minus y over our 0.0325 minus x. But then this is where a lot of assumptions are made. And so you can get rid of the y and the z here. So just assuming that this change is really small. So you can get rid of the y's and z's based off of this equilibrium factor. So the 10 to the negative 3, this is not as clear. So this is kind of why we'll see how we leave it with x and do the quadratic. But then this factor, so we're looking at a 10 to the 5th difference. So that's pretty large. Same with this one, right? That's another 10 to the 5th. So those are pretty large. And so that's why we can get rid of this plus y plus z factor. So then that simplifies to x squared over 0.0325 minus x. Yeah, and we probably don't want to assume that we can get rid of the x, because like I said, it's kind of on that edge there. So we probably have to do the quadratic. Yeah. So we'll go calculator time for this one, since now we only have the few and the brave right here. So what do we get for x? And you can plug it into Wolfram Alpha too.
There's a video on YouTube that shows me how to set up the solve the
Oh,
calculation.
nice. You should definitely share that with me, and I can share with the class too. I'm sure you can. I am not an analytical chemist by training, but if they get really into it, like, yeah, it is just like a series of like equations. So if you don't want to make approximations, yeah, definitely take analytical chemistry, and you'll have a fun time or not fun time.
Depending on who you are, you'll either have a fun time or an awful time.
Yeah. I remember when the TAs, when I took it, were confused, so that's always a good sign. But I feel like you're starting to learn that's like your science classes. So your instructor may be confused. So when I plug it into Wolfram Alpha, so I get two possible solutions for x. One of them is negative, so that doesn't make sense. The other is this 0.0119, and so that looks good. And again, you could go through the quadratic. I'm just saving a little time, because we really want to see all this equilibrium stuff, not quadratic equation 1,000 times. So we get this for x. Okay, so now where do we go from here? So now we have to tackle our next equilibrium issue. And so now let's look at step 2, and we have x, so that helps us. And so now we can set our equation. Let me switch colors, although now it wasn't consistent. Sometimes I upset myself, but that's okay. Go purple, so then 6.16 times 10 to the negative 8th is equal to, so same thing, x plus y plus z times y minus z over x minus y. And so this is again where you simplify so we can get rid of the z, get rid of the y factor, and then this just simplifies to x as well, so ignoring that. So now you have x times y over x. And so now we can just say y is equal to our equilibrium constant. So that is solved.
So the reason we're able to get rid of the negative y in the denominator is just with the 5% rule.
Yeah, yeah. So I'm just comparing our x and then minus y, and then again appreciating the factor of difference. So
That's probably how I was trying to figure out this kind of problem at one point on my own.
yeah,
Just doing it with mostly just x stuff and like just making a new x every time.
yeah,
Like, doing it in each step instead of like doing it all at the same time, kind of. And I got very, very close with the pH, but not with the concentrations because it basically kind of went to zero at the end. So, but I think the reason why I got so close is just because it ended up being low enough that those values didn't really matter. So even if I did it slightly wrong, those ones didn't matter.
yeah.
Why is it that the x plus y plus z term, basically we assume that the y and the z term, instead of just only the y term or the z term, are negligible, but we're not making the same assumption for the y minus z term? Is it because the y is a product with the bigger, more substantial x?
Yeah. Yeah, so you explained it all, right? So we're saying our x is so much bigger that y and z that we don't care. But yeah, we need the product, just like you were saying. But since this difference is small, we got rid of that. Same thing with, again, here. So a lot of simplification. But yeah, you're right in that the next step of this class would be express everything in like a bunch of systems of equations, and then, watch that and monitor that more closely.
Okay, so that would be like if you couldn't assume anything, then
Right, so
just
that's,
log the system.
yeah, that's what the next level
Okay.
is. It's just a bunch of systems of equations, and then you're probably like trying to monitor species and then plug things in, so. So that's analytical chemistry, yeah. There's like usually specific chem class where you.
Don't scare me with that, because I don't want to be. I already have to take organic chemistry. I don't even know that I have to get that specific with organic chemistry, but I probably still will have to get very specific. Well, if you're going to do microbiology, I don't know. I mean, you can if you want. Oh, no, I will, eventually. Eventually. Yeah, they call the chemistry classes. Well, you're gonna have to.
And then just finishing up at the end, so we're here, and then so now we make assumptions again. So just like before, we'll get rid of the addition products, but we need the multiplication. So then that leaves us with x times z over y. And now we have our values, right? So we have x, we have y, so now we can solve for z. So that's just the last step at the end. So x of z over y. So I get this for z once I'm done. I see nods. So z 2.48 times 10 to the negative 18. And so then you can go back and calculate everything. So this is essentially right, your phosphate, you can do the math to do, right, y minus z for this one. Of course, right now we're seeing z is so small that you probably don't even need to do the math, so it's essentially equal to y with our HPO4 species. And so same thing with H2, PO4, so you can do x minus y, but again, that pretty much gives you x. So you can kind of see that. And then you could plug in, so x plus y plus z at the end, although I'm assuming that it gives you a pretty close pH to x anyways. Yeah, because I have 1.92 in the answer, which is essentially just the negative log of x anyways, which is kind of what you find is the other dissociations are really small.
So is this kind of a typical trend for like diprotic and triprotic acids to where, like, say, further iterations, it doesn't really have much of a yield? So usually it's like the first dissociation.
Yeah.
Is pretty much where the pH would lie.
Yeah, and that's like always usually the strongest dissociation. Yeah, for that reason. Cool. I think that's about it. I don't see any questions online, but I'll still hang around. And then, of course, y'all can ask me stuff. I'll probably shut down the official stream soon. But then, yeah, I'm free all afternoon if people have questions or whatever, want to talk about papers or anything else. All right, thanks again. I'll sign off online, and then I'll probably migrate to lab for anybody else that's here.